Physics is broken. The universe is expanding at two different speeds, and nobody knows why. Imagine measuring the width of a room from two different corners, with two perfectly calibrated tape measures, following two rigorous methods verified dozens of times. And you get two results that don't match. Not by a few millimeters, not because of a handling error, two results that simply should not coexist. You try again. You have others check. You try again. The result stays the same. This is exactly what is happening right now with the physics of the entire universe. Two teams of scientists, among the best in the world, are measuring the same thing, the rate at which the universe is expanding, using two different methods. And for a decade, they have been getting two numbers that don't agree. Not slightly, not within the margin of error. Two numbers that cannot both be true at the same time, in the same universe. What makes this situation terrifying for cosmologists is not the gap itself. It's that the more they measure, the more precise both results become, and the further apart they drift. Science is not converging, it is diverging. And physicists are beginning to admit what many of them refused to say out loud just a few years ago. Our model of the universe may be fundamentally broken. This is not a question of imperfect measurement. This is not a question of faulty calculation. This is a question of physics. The very laws governing the entire universe since the Big Bang could be incomplete, or worse, incorrect. More than 500 researchers have joined forces in a global consortium to attack this problem. The James Webb Space Telescope has been mobilized to verify the data. Entire satellites have been built to solve this enigma, and every time, the answer is the same. The problem is real. It is not going away, it is deepening. Today, we are going to dive into this mystery, from Edwin Hubble's first observations in 1929 to the most recent results of 2025. We will understand why two numbers, which seem so close to each other, may represent the greatest crisis in modern physics, and we will explore what scientists really think is happening in the depths of space-time. If you want to stay up to date with every mystery we explore, the universe is full of surprises that exceed imagination. Subscribe to the channel and hit the like button. Every week, we dive into the questions that keep us up at night. And tell me in the comments, which city are you watching from, and what time is it where you are right now? To understand why a disagreement between two measurements can shake all of physics, you first need to understand what the expansion of the universe really means, because this idea is far stranger and far deeper than what one might imagine at first glance. Picture a raisin inside raw bread dough. As the dough rises, the raisins don't move through the dough itself swells. Each raisin moves away from all the others, not because it is moving, but because the space between them is growing. If you were a tiny insect sitting on one of those raisins, you would see every other raisin receding from you in all directions. The farther the raisin, the faster it moves away. Not because it runs faster, but because there is more dough between you and it to swell. This is exactly how the expansion of the universe works. Galaxies are not hurtling through space. It is space itself that is stretching between them. The distance between galaxies grows because the very fabric of space-time is expanding. This concept has a direct and beautiful consequence. Light traveling through this expanding space is itself stretched. Light waves lengthen. They shift toward red, toward longer wavelengths, like stretching a spring. This is called redshift, and it is precisely through this phenomenon that astronomers can measure how fast a galaxy is moving away from us. The more pronounced the redshift of its light, the faster it is receding. The light from a distant galaxy is like a letter written on a certain date, but one that the distance has distorted over the course of its journey to us. By reading the intensity of this shift, we read the speed of its recession. Here is where the story gets profound. If you could connect the speed of every galaxy to its distance, you would obtain a mathematical relationship that describes something immense: the rate of expansion of the entire universe. And this relationship, this slope on a graph, is what we call the Hubble constant. It bears the name of one man. It lies at the heart of all modern cosmology, and it is currently at the center of the greatest scientific controversy of our era. Why is this constant so fundamental? Because it does not merely describe how the universe behaves today, it tells us how old it is, how large it is, how it will evolve. It is like the heartbeat of the universe, a single number that reveals the health of the entire cosmic machinery. If this number is wrong, everything we believe we know about the past and future of the universe is called into question. And right now, we have two measurements of this heartbeat that do not agree. But to understand why this is so serious, we must first go back to the origins of this constant, to the nights at the observatory, the photographic plates, and the stars blinking like lighthouses in the cosmic night. It all begins with a woman whose name should be as famous as Einstein's, but who remained in the shadows for decades. Henrietta Swan Leavitt worked as a human computer at the Harvard Observatory in the early 20th century, a title that at the time designated women employed to analyze astronomical photographs because they cost less than men. Leavitt was analyzing stars in the Magellanic Clouds, those satellite galaxies of our own visible from the southern hemisphere. And in 1908, she noticed something extraordinary. Certain stars, called Cepheids, pulsate. They swell and contract rhythmically, like a heart. And Leavitt discovered that the longer the pulsation period of a Cepheid, the longer it takes to complete one full cycle, the more intrinsically luminous it is. It is a direct, simple, beautiful relationship. A Cepheid pulsating over a period of 30 days is far more luminous than one pulsating over 10 days. That may seem trivial, but its implications are revolutionary. Imagine you are in a forest at night, and you see light bulbs in the distance. If you knew exactly what wattage each bulb was, you could calculate how far away it is simply by measuring its apparent brightness. A brightly glowing bulb could be close or very powerful, but if you know its exact wattage, you can calculate the distance. Cepheids work exactly like this. By measuring their pulsation period, we know their true luminosity. By comparing that true luminosity to their apparent brightness in the sky, we calculate their distance. They become cosmic lighthouses, distance markers scattered across the universe. Leavitt had forged the first rung of a ladder that would allow humanity to measure the cosmos. But it was another man who would use this ladder to transform our understanding of the universe, Edwin Hubble. In the 1910s and 20s, a less famous but equally crucial astronomer was laying the groundwork. Vesto Slipher, working at the Lowell Observatory in Arizona, pointed his spectroscope toward what were then called spiral nebulae, fuzzy, distant objects whose nature remained a mystery. By measuring the spectrum of their light, Slipher discovered something unsettling. Nearly all of these objects were moving rapidly away from us. Their light was shifted toward the red, and not slightly. Some were receding at speeds that exceeded anything previously observed. Within a decade, Slipher had measured the velocities of more than 40 of these nebulae. He had the velocities, but he was missing the distances. It was Edwin Hubble who completed the puzzle. Stationed at Mount Wilson in California with the Hooker telescope, the most powerful in the world at the time, he pointed his instrument at the Great Andromeda Nebula in 1923, and in that fuzzy object, he distinguished something precise, a Cepheid, then another, then several more. By measuring their pulsation periods, he applied Leavitt's method, and the result was staggering. The Andromeda Nebula was at a distance that placed it far beyond any possible limit of our galaxy. It was not a nebula inside the Milky Way. It was an entire galaxy, similar to our own, separated from us by an abyss of light that takes centuries to cross the void. The following day, a colleague of Hubble's, Shapley, received a letter describing the discovery. He showed it to a colleague and said simply, "Here is the letter that destroyed my universe." In one sentence, the cosmos had expanded from the scale of the Milky Way to something infinitely larger. But Hubble did not stop there. He combined his Cepheid distance measurements with Slipher's velocity measurements, whose name he did not cite in his 1929 article, which is another story, and he established a remarkable relationship. The most distant galaxies are receding faster. Velocity is proportional to distance. This linear relationship, this slope on a graph, is the Hubble constant. It asserts that the universe is expanding, that this stretching of the fabric of space is uniform, and that it can be characterized by a single number. Ironically, the value Hubble proposed in 1929 was wildly incorrect. His distance calculations were biased because he did not yet know that there were two types of Cepheids with different luminosities. His value was about 7 times too large. It took decades of painstaking work to correct it, but the structure, the conceptual framework, was right. And in finding that framework, Hubble had placed in the hands of cosmological science its most precious tool and its most stubborn puzzle. Because this number, this slope that translates the dynamics of the entire universe into a single figure, would become a scientific battlefield. For decades, two great schools clashed. One proposed a larger number, the other a smaller one. The measurement uncertainties were large enough that both could coexist until the instruments became precise enough for the margins of error to shrink, and the gap itself refused to shrink. The real crisis would begin not when measurements became imprecise, but when they became too precise to ignore each other. And to understand what happened next, we must first understand how modern astronomers measure the Hubble constant, because there are two distinct paths, two methods that start from entirely different premises and that arrive at two incompatible cosmic realities. The first method can be called the ladder method. Imagine you want to measure the height of a building whose top you cannot see from the ground. You start by measuring the height of the first floor using tools you know well. Then, from that first floor, you measure the height to the second, using the first result as your benchmark. Then from the second to the third, and so on, each measurement resting on the previous one. This is exactly how the cosmic distance ladder works. On the first rung, Cepheids. These pulsating stars, whose property Leavitt discovered, allow us to measure distances to relatively nearby galaxies. For the nearest galaxies, astronomers also use the parallax method. The same technique is when you alternately close one eye and then the other to see a nearby object appear to shift against a distant background. By measuring the apparent shift of a nearby star over the course of Earth's annual journey around the Sun, one obtains its geometric distance without any assumptions about its luminosity. These geometric measurements calibrate the nearby Cepheids. On the second rung, Type 1a supernovae. These are stellar explosions of breathtaking power, an entire star disintegrating in a matter of seconds with a luminosity that momentarily outshines the entire galaxy hosting it. What makes these explosions precious to astronomers is their standardizability. A Type 1a supernova occurs when a white dwarf star accumulates matter until it reaches a precise critical mass, always the same mass, dictated by the laws of nuclear physics. This identical mechanism produces each time an explosion with a characteristic luminosity curve. By observing how the brightness of the supernova evolves over time, one can calibrate its exact luminosity. And by comparing that true luminosity to its apparent brightness observed from Earth, one calculates its distance. Type 1a supernovae are visible billions of light-years away. The team that has brought this method to its most refined level is called SH0ES, an acronym that, fully expanded, designates a program designed to measure the Hubble constant with unprecedented precision. Led by Adam Rees, Nobel Prize in Physics, this team has spent years climbing this cosmic ladder rung by rung, reducing uncertainties at every step. And their result, refined year after year, converges toward approximately 73. In unit terms, this means that for every slice of the universe about 3 million light-years wide, the galaxies at its edges are moving apart from each other at about 73 kilometers per second. The second method is radically different in its approach. Instead of directly measuring distances to nearby objects and extrapolating, it goes all the way back to the origins of the universe. It uses the echo of the Big Bang. Approximately 380,000 years after the Big Bang, a blink of an eye on the scale of cosmic history, the universe was so hot and dense that atoms could not exist. Everything was a plasma of particles and photons in constant collision, in a state of perfect equilibrium. The entire universe was opaque, like being at the core of a star. Then, over the course of a few thousand years, the temperature dropped just enough for protons to capture electrons and form the first hydrogen atoms. And at that precise moment, the universe became transparent. Light, freed from its incessant collisions, could finally travel freely. These photons have been traveling through the expanding universe ever since. Stretched by this stretching of the fabric of space, They have lost an enormous fraction of their energy. Their wavelength has been multiplied by about 1,000. They once glowed with the heat of a star. They now bathe the entire universe in radiation barely above absolute zero. This radiation, detected by chance in the 1960s by two Bell engineers who thought they had a problem with their antenna, is the cosmic microwave background, or CMB. This fossilized radiation is remarkably uniform, but not perfectly so. It displays tiny temperature variations, fluctuations so infinitesimal they represent 100,000th of a degree. These variations are the fingerprints of the first structures of the universe, the seeds that would become galaxies and galaxy clusters. The European Planck satellite, which mapped this radiation with stunning precision from 2009 to 2013, allowed cosmologists to read in these variations a wealth of information about the composition and dynamics of the early universe. And here is the beauty and the drama of the situation. By applying the standard model of cosmology to this data, by extrapolating the state of the universe nearly 14 billion years ago forward to today, one can calculate what the Hubble constant should be today. The result from the Planck collaboration, approximately 67. 67, where the SH0ES team gets 73. Take a moment to digest what this means. Two completely independent measurement methods, using entirely distinct physical phenomena, contradict each other. One says 67, the other 73. The absolute difference seems small, about 8%, but in physics, in cosmology, where error margins are meticulously calculated, 8% is a catastrophe. It is not noise, it is a signal. But to grasp how serious this signal is, one must understand when and how scientists realized this was not simply a calculation error. In the early 2000s, the tension between the two camps was real but tolerable. The uncertainty margins of each method were wide enough that the two results nearly touched. One could hope that better instruments would resolve the problem. This is the first stage of the scientific response to an anomaly. Look for the hidden systematic error, something miscalculated, a bias in the data, a flawed rung in the distance ladder. The Hubble Space Telescope mission, the space telescope bearing the name of the great Edwin, was crucial in the 90s and 2000s for measuring Cepheids with unprecedented precision and beginning to reduce the uncertainties on the constant. In 2001, the HST Key project concluded with a value of 72, with an uncertainty of about 10%. That was encouraging. The value fell between the two camps. Then, in 2013, the Planck satellite published its first cosmological results, and the gap widened. The value of 67, obtained from the CMB with remarkable precision, was clearly incompatible with local measurements, which pointed towards 73 or higher. Both teams had reduced their errors, but the values, rather than converging, had drifted further apart. First alarm signal. From 2016 to 2022, Adam Rees's SH0ES team refined its measurements rung by rung. It studied hundreds of Cepheids in dozens of nearby galaxies hosting supernovae, building a distance ladder of unmatched solidity. In 2022, it published its most precise measurement, 73, with an uncertainty reduced to just over 1%, impossible to dismiss. The H0LICOW collaboration, another international group, adopted a completely different approach to independently verify the result. It used gravitational lensing. When light from a very distant quasar passes near a massive foreground galaxy, the gravity of that galaxy deflects it, creating multiple images of the same quasar. If the quasar varies in luminosity, the different images vary with a slight time delay, because the light forming each image has traveled a path of slightly different length. By measuring this time delay and modeling the mass of the lensing galaxy, one can calculate the Hubble constant. The H0LICOW result, approximately 73. Independent of Cepheids, independent of supernovae, and yet the same result. Second alarm signal. The ACT collaboration, Atacama Cosmology Telescope, produced in 2024 a new independent map of the CMB, even more detailed than Planck's. Its result? approximately 68, consistent with Planck, incompatible with local measurements. The gap did not budge. In January 2025, at a meeting of the American Astronomical Society, physicist Dan Skolnick of Duke University took the floor and said plainly what more and more of his colleagues were thinking quietly. He had presented a new measurement of the Hubble constant based on the Coma cluster, using data independent of the usual controversies surrounding Cepheids. Result? 76.5, even further from 67. And in his presentation, Skolnick officially declared that the Hubble tension was no longer simply a tension, it was a crisis. That moment, that change of vocabulary by a single word, said everything. But to truly grasp the scale of the problem, why physicists cannot simply shrug and pick the number they prefer, one must understand what this disagreement means in statistical terms. And this is where the concept of 5 sigma enters the picture. A concept that, once truly understood, reveals why this disagreement is not a quarrel among experts, but a signal that the universe itself is trying to tell us something. In science, every measurement comes with an uncertainty. If you measure the height of a building 100 times, you will not get exactly the same result each time. The results will distribute themselves around a mean value in a bell-shaped curve, a Gaussian distribution. The width of this bell characterizes the uncertainty. A sigma is a unit of that width. Here is how to think about this intuitively. Imagine flipping a coin. If you get heads 10 times in a row out of 10 flips, you begin to suspect the coin is rigged. But that is not proof. With a fair coin, it can happen, rarely. If you get heads 20 times out of 20 flips, suspicion becomes conviction. But it is still not an absolute mathematical certainty. In physics, this intuition has been formalized. We speak of sigma to quantify how incompatible a result is with chance. A 2 sigma gap corresponds to a result that would occur by pure chance only 5 times out of 100. 3 sigma, 3 times out of 1,000. 5 sigma, fewer than 1 time in 3.5 million. In the social sciences, a 2 sigma result is generally considered significant. In particle physics, the discovery threshold is set at 5 sigma. The reason is simple. Physicists work with so much data and run so many parallel analyses that false positives at 2 or 3 sigma are almost inevitable. A very high bar is needed to announce something truly new. And the tension between the two measurements of the Hubble constant has reached 5 sigma. This means the probability that this disagreement is due to a random fluctuation, a statistical fluke, is less than 1 in 3 million. This is not noise. This is not an artifact. It is a real signal. And this is why physicists cannot simply pick a number. Both measurements rest on solid experimental foundations, verified and re-verified by independent methods. If you choose 67, you must explain why all local measurements are systematically biased, and no known reason explains this. If you choose 73, you must explain why all the physics of the early universe produces an incorrect prediction, which would require profound modifications to our cosmological model. There is no easy way out. Both roads lead into the unknown. And now, the real problem. Because if one accepts that the disagreement is real, if one accepts that this is not a measurement error but a fact of nature, then one is forced to ask a deeper question. And that question points directly at the most mysterious ingredient in all of modern cosmology: dark energy. Dark energy is one of the strangest things humanity has ever conceived, and yet we must postulate it to explain what we observe. In 1998, 2 teams of physicists, one led by Adam Rees, the same Rees who leads the SH0ES team today, observed distant supernovae to measure how the expansion of the universe had slowed since the Big Bang. The gravity of all the matter in the universe should gradually break this expansion, like throwing a ball into the air. It rises more and more slowly before falling back down. But the distant supernovae were fainter than expected, more distant than expected. This meant that the expansion, rather than slowing, was accelerating. The universe is speeding up. And this discovery, so staggering that it earned its authors the Nobel Prize, demanded an explanation. That explanation was named dark energy. It is a kind of energy intrinsic to the vacuum of space itself, a property of empty spacetime that drives it to stretch faster and faster. The vacuum is not truly empty. It contains an energy that repels, that accelerates the expansion. Today, this dark energy would make up about 2/3 of the entire energetic content of the universe. In the standard model of cosmology, called lambda CDM, where lambda is the mathematical symbol for this dark energy, and CDM stands for cold dark matter, this dark energy is assumed to be absolutely constant. It is everywhere in space, always with the same density from the beginning of the universe to its end. It does not change. It does not fluctuate. It is like a fundamental property of space itself, a cosmological constant that Einstein had once introduced into his general relativity equations before removing it, an act he called the greatest blunder of my life, but which the universe seemed ultimately to require. This assumption, that lambda is a true constant, immutable, is the central pillar on which the entire prediction of the Hubble constant from the CMB rests. When the Planck collaboration takes its data and projects it forward to today, it assumes that dark energy has always had and will always have exactly the same density. This is what gives 67. But what if that were not the case? What if dark energy were not constant, but evolved over time? If its density changed, even slightly, the history of the universe's expansion would be different from what lambda CDM predicts, and the Hubble constant calculated from the CMB would be skewed. It would not reflect the true current value, but a value based on an incorrect assumption. And this is where extraordinary data have begun to arrive. In April 2024, the Dark Energy Spectroscopic Instrument, DESI, published the results of its first year of observations. DESI is a monumental instrument installed at the Kitt Peak National Observatory in Arizona, 6,000 optical fibers that can simultaneously point towards 6,000 galaxies and measure their spectra. In a single night, it collects more data than an entire astronomer's career produced in Hubble's era. Its objective? To measure the large-scale structure of the universe with enough precision to detect a slight evolution of dark energy over time. The 2024 DESI results were a bombshell. By analyzing how galaxies are distributed in space across different cosmic epochs, by reading into this distribution the imprint of acoustic waves that traveled through the early universe billions of years ago, the researchers found hints that dark energy may not be constant, that its density could have evolved. At a statistical confidence level of nearly 4 sigma, below the 5 sigma threshold, but already very serious. And in March 2025, DESI published the results of its second data release. 3 complete years of observations. The signal had strengthened. The preference for a dynamic dark energy, one that changes over time, reached 4.2 sigma. The DES team, which had independently analyzed its own supernova data, found 3.2 sigma in the same direction. ACT found hints in the same direction. Multiple instruments, multiple teams, multiple methods, all pointing in the same direction. Dark energy may not be the immutable constant that had been assumed. What is fascinating and deeply troubling at the same time is that even if dark energy is dynamic, this does not automatically resolve the Hubble tension. Modifying the dark energy equation of state can explain some aspects of the disagreement, but the numbers do not fit together cleanly. It is not a clean solution. It is a seam, not a closure. The universe is telling us something is wrong with our model, and dynamic dark energy may be part of the answer, but probably not the complete answer. What this means is that the physics governing the universe is richer, more complex, and more surprising than anything we have understood so far. And this suspicion goes well beyond dark energy. The data from the most powerful telescopes humanity has ever built point towards something nobody predicted. And here is that data, because this is where the story takes an even more unexpected turn. The James Webb Space Telescope was launched in late 2021 with a mission that went far beyond observing distant galaxies. For many, it represented the secret hope of dissolving the Hubble tension by finally finding the hidden error in the data of its predecessor. Would decades of measurements by the Hubble Space Telescope turn out to be tainted by an imperceptible systematic bias? Webb was there to check, and what it found left no room for doubt. The feared problem was simple to state. When you observe Cepheid stars in distant galaxies with the Hubble Space Telescope, the stars are projected onto an increasingly crowded sky. The more distant the galaxy, the more stars overlap in the image. A distant Cepheid may be visually contaminated by the light of a neighboring star, which artificially inflates its apparent luminosity and distorts the distance measurement. This __quote_8__ effect had been identified as a potential source of error, and some researchers hoped it was enough to explain the gap between 67 and 73. Webb, with its unmatched infrared sharpness, was meant to separate what had been blurred. Its primary mirror measures 6.5 meters in diameter, nearly 3 times that of Hubble. In the infrared, it sees through veils of interstellar dust and isolates individual stars with a precision Hubble could not reach. The comparison would be decisive. In 2023, the first Webb observations of Cepheids in nearby galaxies were published. Result? The Hubble measurements were correct. The stellar crowding that everyone worried about was real, but its effects were far smaller than feared, insufficient to explain the gap. In 2024, the SH0ES team published the results of its largest Webb study, covering 5 supernova host galaxies with more than 1,000 Cepheids, extending to the most distant galaxy where Cepheids had been precisely measured. The value Webb obtained for these galaxies? 72.6. The value obtained by Hubble for the same galaxies? 72.8. Agreement to within less than 2%, far below the magnitude of the tension itself. Adam Rees summed up the situation in one sentence. __quote_9___. The title of the scientific paper was unambiguous. Webb's observations reject stellar crowding as an explanation of the Hubble tension, with a confidence level of 8 sigma. 8 sigma. That is near absolute certainty in physics. The problem is not in our instruments, it is in the universe itself. For their part, DESI and Euclid provided a third perspective. The Euclid telescope, placed in orbit by the European Space Agency in late 2023, is designed to map the large-scale structure of the universe with unprecedented precision by measuring the shape and distribution of billions of galaxies across billions of light-years. Its ability to constrain dark energy independently of the CMB and the local distance ladder makes it a valuable arbiter. Euclid's first data publications in 2024 confirmed consistency with CMB measurements, a low value of the Hubble constant, while showing subtle tensions in the large-scale structure of matter that do not fit neatly within the standard model either. This overall picture is disturbing in a particular way. It is not a single instrument producing an anomalous result. It is not a single team with a biased approach. It is a convergence of independent data, obtained by entirely different methods, all pointing in the same direction. The model is incomplete. But incomplete in what way? And is something missing in the early universe, the late universe, or both? This is where the hypotheses take on the character of cosmic exploration, each revealing a different facet of what physics might be hiding. The first major attempt at an explanation is also one of the most audacious. It is called early dark energy, often referred to by its initials EDE. The idea is elegant in its construction. What if dark energy did not exist only today, but it also existed briefly in the very young universe, a few thousand years after the Big Bang, before disappearing? To understand why this would change everything, one must understand what is called the sound horizon. In the first few 100,000 years after the Big Bang, the universe was a hot plasma in which matter and light formed a single fluid. Sound waves traveled through this fluid like waves crossing a body of water. These waves propagated until the universe cooled enough for matter and light to separate. At the moment of recombination, about 380,000 years after the Big Bang. At that moment, the sound waves were as if frozen in place, their final size being what is called the sound horizon. This sound horizon is a cosmic ruler. Its size, about 500 million light-years in today's universe, is one of the fundamental calibrators that allows the CMB to predict the Hubble constant. The Planck collaboration measures the apparent size of this ruler in the sky and deduces the distance to it, which directly constrains the value of the Hubble constant. The larger the ruler in reality, the smaller the deduced Hubble value. This is where early dark energy comes in. If, in the very first moments of the universe, just before recombination, there existed an additional energy field contributing about 5% to the total energy density, the universe would have expanded slightly faster during that period. This would have shrunk the sound horizon. The cosmic ruler would have been smaller, and a smaller ruler means that to explain the same apparent size observed in the CMB, the universe must be closer, which implies a faster expansion, which gives a higher Hubble constant, compatible with 73. The beauty of this hypothesis is that it acts exactly where needed, on the physics of the early universe, so that CMB measurements would predict a larger number. It does not interfere with local measurements. It would reconcile the two camps, and it is grounded in well-established theories of field physics, notably theories involving scalar fields, axions, or fields inspired by string theory that could naturally exist without any modification of known laws. Teams at MIT and other institutions even showed in 2024 that this early dark energy could simultaneously resolve a second mystery raised by Webb, the presence of massive, luminous galaxies too early in the history of the universe. Webb has observed galaxies as developed as our Milky Way, when the universe was only a few 100 million years old. In lambda CDM, galaxies form progressively, like cities that grow slowly. Early dark energy would modify the parameters of structure formation in a way that would allow these early massive galaxies. One model for two problems. Exactly the kind of theoretical economy physicists love. But early dark energy has a serious problem. It resolves the Hubble tension, but amplifies it in exchange in another domain, the clustering of matter. By modifying the dynamics of the early universe, it predicts a greater abundance of large-scale structures than what is actually observed. This creates a new tension, the S8 tension, between EDE predictions and gravitational lensing surveys. Fixing one problem creates another. Most cosmologists, therefore, remain skeptical of EDE as a complete solution, even though it remains one of the most studied options. There is yet a deeper layer to the same question. What if the problem came not from dark energy, but from dark matter itself? This is the second major hypothesis, and it touches on one of the most mysterious ingredients of the cosmos. In the lambda CDM model, dark matter is cold. This qualifier designates particles that move slowly relative to the speed of light at the time of structure formation. These particles interact with each other, and with ordinary matter only through gravity. They form halos in which galaxies nestle. They create the cosmic web of filaments and voids that structures the observable universe. But the exact properties of these particles are unknown. What if they were not exactly as the model assumes? Warm dark matter, first of all, is a variant in which dark matter particles move faster. Candidates, such as light sterile neutrinos, would be warm or tepid. Their behavior in the early universe would be slightly different from that of cold dark matter. They would not form small structures as easily, modifying the large-scale distribution of matter. These modifications directly affect baryon acoustic oscillations, this cosmic ruler imprinted in the distribution of galaxies, and can shift the value of the Hubble constant deduced from them. But the most intriguing version of this hypothesis is interacting dark matter. Imagine that dark matter is not quite as solitary as once thought, that it interacts slightly with itself, or with photons, or with other particles in the dark sector. Even tiny interactions in the early universe modify the way sound waves propagate through the plasma. They change the characteristic wavelength of baryon acoustic oscillations. And if they change the sound horizon, they change the CMB's prediction of the Hubble constant. Studies combining Planck and DESI data have shown that models of interacting dark matter can reduce the Hubble tension to below 2 sigma, nearly making it vanish, while remaining compatible with other cosmological observations. The key is that the interaction between dark matter and dark energy can modify how cosmic distances are related to the expansion rate, shifting the Hubble constant in the right direction. Some models reach a value of 70 to 71, halfway between the two extremes, with a statistical plausibility that deserves to be taken seriously. To put this in a concrete image, imagine that the early universe was a vast basin of water into which thousands of pebbles were dropping simultaneously, creating waves that crossed and overlapped. These waves, the baryon acoustic oscillations, propagated through the plasma, and left an imprint in the distribution of galaxies we see today. The size of this imprint, the sound horizon, depends directly on how fast the waves could propagate, and therefore on the density and interactions of the components of the primordial plasma. If dark matter does not behave exactly as lambda CDM assumes, if it slightly slows the waves or modifies their propagation speed, then the imprint would be slightly different, and the Hubble constant deduced from it would be different. Results published in Physical Review Letters in 2024 showed that models of interacting dark energy, calibrated on combined DESI and Planck data, produce a value of the Hubble constant around 70.8, reducing the tension with SH0ES to below 2 sigma. That would be almost a reconciliation, but other analyses of the same data arrive at opposite conclusions. The models are sensitive to data choices, statistical priors, and analysis methods. This battlefield between rival teams is precisely the terrain on which truth will have to emerge. The problem with these dark matter hypotheses is their deeply unverifiable nature in the short term. Dark matter is not directly detected. Its properties are constrained indirectly through structural observations. Adding interaction parameters to a model that already contains many degrees of freedom is a path that risks creating more questions than it resolves. And for now, no direct detection of interacting dark matter exists, leaving these models in the state of plausible but unconfirmed conjectures. The third hypothesis is of a very different nature. It does not touch the composition of the universe, it touches on our position within it. There is an idea in cosmology that has reassured scientists for centuries, the Copernican principle. The idea that we are not in a special position, that where Earth sits in the universe is mundane, ordinary, representative. This principle underpins all of modern cosmology. When we measure the Hubble constant from our corner of the cosmos, we are measuring something representative of the entire universe. But what if that were not true? Not in the philosophical sense of underscore underscore quote underscore 13 underscore underscore. Nobody claims that. But in the more subtle and verifiable sense, what if our galaxy happened to sit in a region of the universe with a significantly below-average matter density? This is the Hubble bubble hypothesis. In the universe, matter is not uniformly distributed. It forms a cosmic web of filaments and galaxy clusters, between which stretch vast, empty deserts, cosmic voids. If the Milky Way sits inside one of these voids, a region several billion light-years across with the density roughly 20% below average, then galaxies at the edge of this void would be gravitationally attracted toward denser regions outside, moving away from us faster than they would in a uniform universe. Result? Our local measurement of the Hubble constant would be artificially inflated. We would measure 73, while the true global value would be close to 67. This void even has a name. It is called the KBC void, after the astronomers Keenan, Barger, and Cowie, who mapped it in 2013 by counting galaxies in the nearby universe. They found a density about twice below the cosmic average, extending over a radius of about 1 billion light-years. The Milky Way sits a few 100 million light-years from the center of this void. What this means in practical terms, galaxies at the edge of this void are gravitationally drawn toward the denser regions outside. They are, quote, 14 the void. Seen from our central position, they therefore appear to be receding faster than they would if the matter distribution were uniform. Imagine standing at the center of an empty arena, surrounded by dense crowds in the stands. Everyone in the stands appears to be moving away from you. From your perspective, you would measure an underscore underscore quote underscore 15 underscore underscore faster than someone positioned in a more uniform area. This is exactly the effect of the KBC void on our local measurements of the Hubble constant. In July 2025, at the Royal Astronomical Society's annual meeting in Durham, astronomer Indranil Banik of the University of Portsmouth presented an analysis that caused a sensation. By compiling 20 years of BAO, baryon acoustic oscillation, measurements, and comparing models with and without a local void, he obtained a stunning result. A cosmological model incorporating this void is about 100 million times more probable than the standard lambda CDM model without a void for the same BAO data. This is not a slight preference, it is an overwhelming preference in Bayesian statistics. If the KBC void is real and as extensive as the data suggest, it would naturally explain why our local measurements overestimate the Hubble constant. Without modifying the laws of physics, without introducing new exotic particles or fields, simply by recognizing that we live in a particular corner of the universe. The problem is that the KBC void, as described, is itself difficult to reconcile with lambda CDM. In the standard model, matter should be distributed fairly uniformly on large scales. A void this extensive and this deep represents a density fluctuation so extreme, it would be nearly impossible within the lambda CDM framework. This creates an embarrassing circular situation. The void resolves the Hubble tension, but creates its own tension with the standard cosmological model. One might need a different gravitational physics, a stronger gravity at large scales that would allow such voids, to make the whole thing coherent. Other teams contest the existence of the KBC void. Dan Skolnick and his collaborators, for example, have analyzed supernova data to test whether the Hubble tension diminishes with distance. If the void were the cause, local measurements should progressively converge toward the CMB value when looking beyond the void, which they do not find. The tension persists at all distances tested, which argues against the void as the sole explanation. This debate remains open and vigorous in 2025. Additional data from Euclid, DESI, and future galaxy mapping missions could settle it within a few years by directly testing the large-scale matter distribution around us. But even if the KBC void is confirmed, the deeper question remains: why is it there? Why is it so deep? And is it sufficient to explain the entire tension, or only part of it? All these hypotheses, early dark energy, interacting dark matter, the cosmic void, have in common that they remain within the general framework of known physics. They propose adjustments, additional parameters, different configurations of already postulated ingredients. But the fourth hypothesis does not have this restraint. It touches something far deeper. It suggests that the laws themselves are incomplete. If the first three hypotheses represent touch-ups to the existing picture, the fourth asks whether the picture needs to be repainted from scratch. Not an adjustment to standard cosmology, but a challenge to the very foundations that support it. That may seem extreme, but the history of physics is full of moments where what seemed a slight anomaly turned out to be the signal of a revolution. The most radical avenue currently being explored touches on gravity itself. Einstein's general relativity, verified to staggering levels of precision in the solar system and in the gravitational waves of merging neutron stars, may be incomplete at cosmological scales. Modified gravity theories propose that Einstein's equations require a correction when applied to distances spanning the entire universe. The Mond theory, modified Newtonian dynamics, originally developed to explain galaxy rotation curves without dark matter, and its relativistic extensions offer an example of gravity that behaves differently at large scales. Within this framework, the growth of cosmic structures would be accelerated relative to what lambda CDM predicts, allowing voids as deep as the KBC and a higher local Hubble constant. Other theories, such as scalar tensor gravity or FR models, modify the fundamental equation of general relativity by adding terms that become important only at large cosmological distances. These modifications change the expansion history of the universe, and with it, the prediction for the Hubble constant. The appeal of these theories is that they preserve all known physics in the regimes where it has been tested: the solar system, neutron stars, gravitational waves, while modifying predictions at scales we have not yet been able to probe with the same precision. This is precisely where general relativity has never been directly tested, over millions of light years in an expanding universe. Generalizing our laws to these scales is an extrapolation, an admirably confirmed extrapolation so far, but an extrapolation nonetheless. Another even bolder avenue: extra dimensions. If space-time has hidden dimensions, compactified at scales too small to be directly observed, gravity could behave differently at those scales. Gravitational force, which propagates through all available dimensions, would become weaker at large distances than it would in a purely four-dimensional space. These modifications to the propagation of gravity would leave imprints on the expansion history of the universe, imprints that could, in principle, shift the Hubble constant. But the avenue currently attracting the most theoretical attention may be interaction between the dark sector. What if dark matter and dark energy, treated as completely separate entities in lambda CDM, were in fact interacting with each other? This would change how dark energy evolves, which would modify the expansion history of the universe from the Big Bang to today. Models of interacting dark energy, IDE, show promising ability to reduce the Hubble tension in certain configurations, but at the cost of considerable theoretical complexity and a freedom of parameters that makes them difficult to falsify. There is also an idea that few dare to voice out loud, but that some theorists do not entirely exclude. What if the fundamental constants of physics, such as the speed of light or the gravitational constant, were not absolutely constant on cosmological scales or over cosmological time? A variation in the speed of light between the early universe and today, even infinitesimal, would shift the ratio between optically measured distances and true cosmological distances. It would shift all CMB predictions in a way that might reconcile the two measurements. These theories are speculative and heavily constrained by existing data, but they are not mathematically impossible, and some researchers are exploring them seriously. What is troubling about all these hypotheses is that none stands out clearly. Each resolves part of the problem while creating or aggravating other tensions. EDE worsens the S8 tension. The KBC void is difficult to create in lambda CDM. Modified gravity must navigate around decades of precise verifications. Physics beyond the standard model of cosmology is an open, rich, and frustratingly unresolved space of options, none yet verified. And more than 500 researchers gathered in the Cosmoverse Consortium, the largest collaboration ever formed to tackle this problem, have arrived at a remarkably sober conclusion. There is no simple solution. There is no theoretical silver bullet. The resolution of the Hubble tension will likely require a combination of new physics in both the early universe and the late universe. Not a fix, but a rethinking. What this implies for fundamental physics is dizzying. Because if we need new physics at two different epochs of cosmic history, there is a good chance that this new physics will have profound consequences for what we understand about space, time, matter, and energy, the four building blocks of everything that exists. And this is precisely where the most recent data from DESI and other instruments come into play. Because these data do not merely point to an anomaly, they point to something specific, something that can be quantified, something that has a name few physicists expected to have to pronounce with such seriousness. That name is phantom energy. And to understand what the 2025 DESI data truly reveal, one must first understand what this term means and why it worries theorists so much. In the standard model, dark energy is characterized by what is called its equation of state. This is a number, denoted W, that describes how the pressure of dark energy relates to its density. For a cosmological constant, for the static and immutable dark energy of lambda CDM, this number is exactly -1. That is the boundary case, the frontier. If W remains strictly equal to -1, lambda CDM is correct, and the universe expands at a uniform rate dictated by this constant. If W is slightly greater than -1, if dark energy is slightly slower than a constant, we enter the regime of quintessence, a dynamic scalar field that is physically reasonable. But if W drops below -1, we enter territory that theoretical physics considers deeply problematic. This is the phantom energy regime, an energy whose density increases with the expansion of the universe instead of remaining constant or decreasing. Imagine a fluid whose pressure is so negative that it swells as space stretches. The more the universe expands, the denser this fluid becomes. The denser it becomes, the faster it accelerates the expansion, and so on, in a rising spiral toward a conclusion physicists call the Big Rip, where the expansion accelerates so much that it ends up tearing not only galaxies, but stars, then planets, then atoms, then space-time itself apart. Phantom energy is theoretically unstable. The fields that produce it violate fundamental principles of particle physics, notably what is called the null energy condition. Most theoretical physicists regard it as a mathematical curiosity, not a physical reality. And yet, this is precisely where the DESI data point. In March 2025, the DESI collaboration published the results of its second data release, based on 3 complete years of observations and more than 14 million galaxies and quasars. It is the largest catalog ever used to measure baryon acoustic oscillations. The precision of the cosmic ruler measurements exceeded anything done before, a precision below 1% at certain redshifts. When this data was combined with that from the CMB and several supernova catalogs, the signal sharpened. The preference for dynamic dark energy, which changes over time, reached 4.2 sigma. What is striking about this signal is its specific behavior. The data suggest that dark energy was stronger in the past and is weakening today. In technical terms, this corresponds to a parameter W that would have been below -1 in the past and would have risen back above -1 more recently, crossing the phantom divide, this line at -1, in a direction not expected by simple quintessence models. Extended analyses by dozens of researchers using independent statistical methods, Gaussian process approximations, redshift binning, various parameterizations, all reach the same conclusion. The trend is robust. The scientific community is cautious, as it should be. 4.2 sigma is serious, but it is not 5 sigma. There remains a probability, small but non-zero, that this signal is a statistical fluctuation or the expression of an unidentified systematic bias in the supernova data used for calibration. The Atacama Cosmology Telescope team finds only weaker hints in the same direction, and specific models of classical quintessence, which do not allow crossing the phantom divide, fit the data considerably less well than more general models. This is not a certainty, but it is a persistent signal, consistent across methods, that has strengthened with each new dataset since 2024. What this implies for the Hubble tension is subtle. A dark energy that evolves modifies the expansion history of the universe between the Big Bang and today, which could in principle modify the value of the Hubble constant inferred from certain measurements. But analyses show that the modifications due to this dynamic dark energy do not directly resolve the Hubble tension in a clean and complete way. They add complexity without closing the case. What the DESI data are telling us with increasing force is that lambda CDM in its simplest form is very likely incomplete, and that the incomprehension of dark energy is not merely quantitative, but qualitative. We do not understand what dark energy is, whether it changes, or why. And this ignorance, combined with the Hubble tension, looks more and more like 2 symptoms of the same disease whose cause we have not yet diagnosed. More than 500 researchers in the Cosmoverse Consortium, who produced a cosmology white paper in 2025, concluded that the problem is now serious enough to warrant a systematic reconsideration of the assumptions underpinning all of standard cosmology, assumption by assumption. No panic, no spontaneous revolution, but a disciplined, rigorous questioning of an edifice that had seemed so solid. And this is not the first time physics has found itself in this position. There is one thing that the history of physics teaches with remarkable consistency. Great crises are never the end. They are always the beginning. At the end of the 19th century, physics seemed nearly complete. Newton's laws governed the motion of planets with extraordinary precision. Maxwell had unified electricity, magnetism, and light in an elegant theory. Thermodynamics described heat and energy with impeccable mathematical rigor. In 1894, the American physicist Albert Michelson, who would become a Nobel laureate a few years later, publicly declared that the fundamental laws of physics were essentially all discovered. It remained only to refine them, to calculate a few more decimal places. And then came 2 anomalies that did not fit the picture. 2 small clouds, as Lord Kelvin called them in a famous lecture in 1900, on the horizon of an otherwise serene physics. The first cloud was the behavior of hot bodies. All of classical physics predicted that when a body is heated, it should emit an amount of energy that increases indefinitely at high frequencies, an infinite energy catastrophe at short wavelengths. Laboratory furnaces, stars, everything that glows, their behavior contradicted the theory. The anomaly was real, robust, impossible to explain by any minor correction to existing equations. It was called the ultraviolet catastrophe. In 1900, Max Planck found a radical mathematical solution. For the equations to work, one had to assume that energy was not continuous, that it came in small, discrete packets, quanta. Planck himself did not believe this described reality. He thought it was a computational trick. A few years later, Einstein took this same concept and used it to explain the photoelectric effect. And from this small anomaly of hot bodies, from the universe's refusal to conform to classical predictions, the whole of quantum mechanics was born. The most profound revolution in modern physics, which today gives us the transistors in our phones, the lasers in our screens, the MRI scanners in our hospitals. The second cloud was the orbit of Mercury. Since 1859, astronomers had known that the point of Mercury's orbit closest to the Sun, its perihelion, did not remain fixed as Newton predicted. It advanced slightly with each revolution, shifting by a tiny but precisely measurable amount. The astronomer Urbain Le Verrier, who had brilliantly predicted the existence of Neptune by analyzing perturbations in Uranus's orbit, sought the same explanation for Mercury. Perhaps an as-yet unknown planet, closer to the Sun, was causing this anomaly. It was called Vulcan. It was searched for over decades, notably during solar eclipses, which allowed observation of the sky close to the Sun. It was never found. In 1882, Newcomb recalculated the perturbations due to the known planets and confirmed the anomaly. There remained an irreducible excess of 43 arcseconds per century that Newton could not explain. 43 arcseconds per century. If you were standing on the Sun and pointing your finger at Mercury's perihelion, over 100 years, your finger would have shifted by an amount you could not perceive with the naked eye in the sky. It is infinitesimal, and yet, this infinitesimal deviation was real. It was measured, and it fit no known framework. In 1915, Einstein published the theory of general relativity. In this revolutionary framework, where gravity is no longer a force but a curvature of space-time, Mercury's perihelion advanced by exactly 43 arcseconds per century. Not approximately, exactly. Einstein wrote to his friend Michele Besso a letter in which he described something unusual for a scientist of his stoicism. The motion of Mercury's perihelion is explained quantitatively. I remained for a few days in joyful exultation. An anomaly of 43 arcseconds, a deviation so small it seemed almost trivial, had triggered a revolution that redefined our understanding of gravity, time, and the nature of space itself. Newton's mechanics was not wrong. It was an approximation of a deeper theory, an approximation valid in the regimes where it had been tested, but incomplete at the limit. The Hubble tension today occupies the same structural position in physics as those two clouds at the turn of the 20th century. It is a robust anomaly, verified by independent methods, that resists all attempts to explain it away as a measurement error. It is not a terminal crisis. It is an invitation. Physics, every time it has encountered an anomaly of this nature, has not retreated. It has advanced towards something greater. Quantum mechanics emerged from a thermal anomaly. General relativity emerged from a disagreement of 43 arcseconds per century in the orbit of a planet. These are crises that produced the two pillars on which all of modern physics rests, and which, paradoxically, still refuse to unify with each other. If the Hubble tension contains, hidden within its two stubborn numbers, a clue toward the physics of the 21st century, the history of science suggests that what emerges from it will surpass everything we can imagine from our current vantage point. What the Hubble tension tells us, in the final analysis, is something of vertiginous philosophical depth. It tells us that the universe, observed from its beginnings and observed from its present state, contradicts itself, not anecdotally, not marginally, but with a precision of 5 sigma on the most fundamental property there is, its own rate of unfolding through space and time. This means that something in our description of the universe is fundamentally incomplete. Perhaps lambda CDM, this model that has served us so well for 25 years, is what Newton was to Einstein, a remarkably precise approximation within tested regimes, but missing something essential at its foundations. If that is the case, modern cosmology stands at the dawn of a transformation of the same order as the quantum revolution or the relativistic revolution. Not incremental improvement, a conceptual overhaul. Consider what this implies concretely. All the maps of the universe we have drawn, all the simulations of galaxy formation, all the models of 14 billion years of cosmic evolution, all the scenarios about the age, size, and fate of the cosmos rest on the parameters of lambda CDM. If the foundations shift, these maps will have to be redrawn. This is not nothing. It is the entirety of our cosmological worldview, reconstructed from its roots. The theoretical alternatives that are emerging have implications that reach beyond cosmology. If dark energy is a dynamic field, an entity that evolves and interacts, this raises fundamental questions about the nature of the vacuum. What is the quote 20 of spacetime? If it contains an energy that changes with time, this vacuum is not simply nothing. It is something with a structure, a history, a dynamics of its own. Particle physics, general relativity, and observational cosmology are then forced toward a unification that decades of attempts have not yet achieved. If gravity behaves differently at large scales, if Einstein's equations are only an approximation of a deeper theory, then the entire structure of the observable universe, from the way galaxies form and organize to the nature of space-time itself, will need to be reinterpreted. This is not a minor correction. It is a paradigm shift in the most literal sense of the term. There is something particularly dizzying about the fact that we happen to live at the precise moment when this problem has become acute enough to be seen clearly. For most of human history, we did not even know the universe was expanding. For the majority of the 20th century, we lacked the instruments to measure the Hubble constant with enough precision for the disagreement to become visible. Today, in 2025, we have telescopes in space and in high-altitude deserts, catalogs of tens of millions of galaxies, numerical simulations that compute the evolution of the universe over billions of years. And it is precisely because our measurements have become so precise that the fracture appeared. We are no longer ignorant. We are knowledgeable enough to see where our knowledge stops. What we know with certainty is that the universe is real, that it exists, that it is expanding, and that it is showing us, through two measurements that stubbornly refuse to agree, that our map of the cosmos is incomplete. This is not bad news. It is the best possible news for science. Incomplete maps are the ones that get corrected, and in correcting them, we discover new continents. The Hubble tension is not the announcement of physics's failure. It is the announcement that physics still has unexplored territories ahead of it, and somewhere, in the data of DESI and Euclid, in the infrared images of Webb, in the gravitational waves that LIGO and its successors will capture from merging black holes and neutron stars, in the catalogs of several billion galaxies that the coming decades will produce, somewhere in all of this, the answer is waiting. It is waiting for the moment when a human intelligence will know how to see it. That is the beauty of science, not certainty, the horizon. If you enjoyed diving into this mystery with us, if the question of what the universe hides behind its two contradictory speeds fascinates you as much as it fascinates physicists around the world, then subscribe to the channel and hit like. Every week we explore the questions that science poses without yet being able to answer. The places where physics leans over the void and whispers that there is something there. And tell me in the comments, which city are you listening from? And what time is it where you are right now? If you wish to support this channel and help us continue producing these explorations, there is a link in the description. You can leave a donation there, however small. Every contribution allows us to prepare the next video, to go further, to dig even deeper. The universe has questions that deserve time and passion, and we have plenty of both.